I welcome everybody to our IMS public lecture given by Jeffrey Shallit from the University of Waterloo, and the title is Adventures in Automata with a Theorem-Prover. Professor Jeffrey Shallit is a professor in the School of Computer Science at the University of Waterloo, where he has taught since 1990. He is a foreign member of the Finnish Academy of Science and Letters. He received his undergraduate and graduate education in California from the Princeton University and the University of California, Berkeley, respectively. And he works about formal languages, finite automata, combinatorics on words, algorithmic number theory, algebra, and history of mathematics. And he is one of the pioneers in automatic complexity, which was the topic of today's invited lecture by Bjorn Kjos-Hansen. And he will talk now about theorem proving with Walnut, a system which he tested on automatic sequences. These are sequences which have certain properties like Axel to a sequence of a binary word, infinite word, which doesn't contain cubes, so no repetitions of the form u for any binary string, which is not empty. Thank you. And now you have the word, Jeffrey.
Okay, thanks very much for having invited me to this very prestigious lecture series. I wish I could be there in person, as I've never visited Singapore, and it would be a great opportunity to see your country, but perhaps someday in the future. So with that, let's get started. I'm going to start with mentioning something that's probably familiar to most of your audience, which is how a lot of us do mathematics. And there's a flow chart here. It says, well, you examine properties of some objects that you are interested in. Maybe you look at lots of examples. Perhaps you generate examples by hand, or you look at a computer program that generates examples, and then you formulate a conjecture. You try to prove this conjecture. If you're lucky, the theorem is proved, and otherwise you might have to go back and look at more examples or formulate other kinds of conjectures. There's a famous anecdote about the mathematician Julia Robinson, who was once asked, could you please describe as a mathematician what you do during your week? And she said, sure. Monday tried to prove theorem. Tuesday tried to prove theorem. Wednesday tried to prove theorem. Thursday tried to prove theorem. Friday, theorem false. So this is some of the frustration of being a mathematician. So this is a familiar research methodology. It's worked for centuries. Disadvantages are you need to be clever. And sometimes this is preposterously difficult if the description that you're trying to understand is very complicated or has a difficult proof. So what I want to propose is a new research methodology. You examine properties of some object, you look at lots of examples, you formulate a conjecture, but in parallel, you're finding some logical theory that's actually decidable. And then you build your software for the decision procedure. You just pass your conjecture into the software, and the conjecture is either proved or disproved. So the advantages to this are you don't need to be very clever, because all the work is done for you by this decision procedure. And sometimes if you don't even know what the conjecture should be, a system could generate the proper conjecture for the objects you're interested in. The disadvantages to this is that it's not going to work all the time. Decision procedures don't exist for most of mathematics. And sometimes when they do exist, the amount of time and space that they require, in the worst case, can be truly, truly astronomical. Okay, well, let's look at some examples of this. Well, if you've ever used a computer algebra system, you may be familiar with the Wilf-Zeilberger approach that can automatically prove combinatorial identities. And this is implemented in many systems, such as Maple or Mathematica. In such a system, you can just put in some sort of summation like this. It could be an infinite summation. It could be a finite summation. Here we have a finite summation that is parameterized by n, and you just type this in the appropriate syntax, and the system comes back and says something like what's on the right-hand side. So if you have a conjecture of what one side equals, you can verify it, and even if you don't know what it is, the system can tell you. Other examples include the use of SAT solvers, which have been recently pioneered. So you may have heard of this thing called the Boolean Pythagorean triples problem. I won't say what it is right now for lack of time, but that was solved using a SAT solver. And then there are other kinds of systems like proof assistants, which in some cases can automatically generate proofs. Here you have to do a lot more work because you have to establish some sort of axiomatic framework for whatever area you're working in, and that can take a very long time and a lot of person hours. But once this is done, in some cases, you can automatically generate proofs of assertions. Okay, so let's go back to history a little bit. So Hilbert, a famous German mathematician, this picture that I have here is from a card that was distributed in the university town of Göttingen that students could buy and send home to their parents to say, I am studying with the great Hilbert. When Hilbert died, there was a torchlight procession in his honor through the streets of Göttingen. Ah, those were the days. And Hilbert's dream was to show that every true statement is provable. And of course, this dream was then killed by Earl. And that perhaps to provide a program that would decide if a given statement is provable. And that dream was killed by Turing. But still, although we can never hope to do this for all of mathematics, some subclasses of mathematics, some subclasses of problems are decidable. And by that, I mean that an algorithm, or you can think of this as a program, exists, which is guaranteed to prove or disprove any statement in the class. So in principle, one can simply type in the statement in an appropriate language and get back either a proof or a disproof. So I'm going to call n plus, with these angle brackets, the set of all first order logical formulas in the natural numbers with addition. So what are we allowed to say in this language? We can use variables like x, y, and z. We can join together statements with logical connectives like and or. We can add natural numbers together. We can write things like x plus y. We can compare them, saying things like x less than or equal to y. And we can use the quantifiers there exists or for all. And probably everybody knows what these are, but just to remind you, there exists says at least one number, in this case, satisfies the assertion that you're saying. And for all, it says every natural number satisfies this. And this system is sometimes called Pressburger Arithmetic. So here's an example of a statement. For all x and y, x plus y equals y plus x. So what does that assert? So probably most of you know immediately that this is asserting the commutativity of addition. It says that it doesn't matter what order you add numbers in, the result will be the same. So in Presberger Arithmetic, that would be true. That would evaluate to true. So let's look at a less trivial example. This is the so-called chicken McNuggets problem. Now, I went on the Singapore site of McDonald's last night, and I downloaded this picture from Singapore McDonald's. And it says that in Singapore, if you go and order chicken McNuggets, then they're available in a 6, 9, or 20-piece package. Those are the only choices. So if these are the only choices, then of course you can never order 5 McNuggets because they only come in 6, 9, or 20. But 5 isn't the only number that you can't order. There are actually other numbers that you can't order. And from a theorem, because the GCD, the greatest common divisor of 6, 9, and 20, is 1, there is some number beyond which you can always order that many McNuggets at McDonald's. But below that, there is some, at that point, that number itself is not orderable. So what's the largest number of McNuggets that one cannot purchase? Well, this is something we can say in Pressburger Arithmetic. So in Pressburger Arithmetic, we can express the Chicken McNuggets theorem. And what does the Chicken McNuggets theorem say? It says 43 is the largest integer that cannot be represented as a non-negative integer linear combination of 6, 9, and 20. So what is that? How do we say that? For all n bigger than 43, there exist integers x, y, and z such that n is 6x plus 9y plus 20z, and there do not exist these integers such that 43 has a representation. So as I've written it, this isn't quite legitimate because I've used multiplication. And in my theory, all I can do is add. But luckily, these numbers 6, 9, and 20 are constants. So 6x is really just shorthand for x plus x plus x plus x plus x plus x 6 times. Similarly for 9y and 20z. But it's kind of tiresome to write that out in full generality. So I use this shorthand. So that's an assertion. So that is a statement in this theory, and we can evaluate this statement. So Pressburger Arithmetic, the name comes from Moses Pressburger, who was a mathematician who was murdered by the Nazis. So unfortunately, his career was cut short. He proved that this logical theory is decidable. The method that he used was something called quantifier elimination, which I won't talk about. And this was an extremely influential master's thesis. At the time, people thought, oh, this is very trivial, but it turns out that it's had a lot of consequences, and a very large number of papers have dealt with the consequences of his result. So I'm going to talk about a different proof of Pressburger's theorem that is based on finite automata. So what are finite automata? Well, finite automata are a model of a computing machine, but a very stupid computing machine, very simple kind. It only has finite memory, and this memory is stored in something called states. So there are a finite number of states. And the inputs of a finite automaton are strings of symbols, sometimes called words, chosen from a finite alphabet. So an input might be something like ABC or 101. So as each symbol is processed, the automaton looks up in a table and decides which state to go to based on its current state and the input letter that it's reading. Now, certain states are called final. So if after you read the whole input, the automaton is in a final state, we say the input's accepted, and otherwise it's rejected. So what you can think of is that this automaton is a device. It has a green light and a red light. You type in your word or string of symbols, and either the green light goes on, in which case it's accepted, or the red light comes on, in which case it's rejected. Now, we can also make a small variation of this model. Instead of just having two possible results, green and red, accept or reject, we could have an output letter associated or number associated with each state. This output that we the last state. Okay, so let's look at an example of an automaton. Here's an automaton with 7 states. And this automaton, you start in the start state and you read the symbols following the arrows. And the double circles are these accepting or final states. So by staring at it, hopefully you can see what kinds of strings are accepted and what are rejected. What we accept are those strings whose first symbol is the same as the last. So let's try a string like 2, 1, 2, 2. And indeed, the first symbol is the same as the last, and I'm in an accepting state. If I try a string like 1, 3, though, I go 1, 3, and I don't have this double circle, so it's not accepted. Okay, let's look at one more quick example. Here's an automaton that actually computes something. It computes n modulo 3, where n is a natural number expressed in base 2. So for example, let's take 21. 21 in base 2 is 10101, and we start here and we read 1, 0, 0, 1, and the result is 0. That's the name of the state, and that's the output. So that says that n modulo 3, 21 modulo 3 is 0, which is correct. Okay, so Bushi came up with a proof of the decidability of Pressburger arithmetic. And his proof represented integers in some base, like, for example, base 2, starting with the most significant digit. And it represented pairs of integers, or in general, t-tuples of integers, as words over a larger alphabet. And this corresponds to reading the base K representations of the numbers in parallel. So, for example, the pair of natural numbers, 21 and 7, can be represented in base 2 by this string of symbols over pairs, binary. So if we look at the first entry of each pair, 1, 0, 1, 0, 1, this spells out 21 in base 2. And if we look at the second component of each pair, it spells out 0, 0, 1, 1, 1, which is 7 in base 2. So this represents the pair of natural numbers, 21 and 7. So what's the idea behind Bushi's proof? It is given a formula with free variables, x1 through xt, we inductively construct an automaton accepting the base K expansions of the t-tuples for which this formula evaluates to true. And for example, suppose we want to check a relation like x plus y equals z. We build an automaton to do this, and this automaton is going to check whether or not there's a carry. And if the digits agree, then we expect there's no carry. Otherwise, if they don't agree and they're off by 1, we're looking for a carry. And we just walk around this automaton, checking the relation bit by bit on the triples of x, y, and z, represented by these individual bits a, b, and c. And if we end up here, then we have indeed verified this relation. Okay, well, we can also check things like x equal y and x less than y with automata. And if the formula is of the form there exists something, then we use a trick that's common in automata. We basically use something called nondeterminism. And what we do is we guess the xi and we check them. And the way we can do this sort of guessing, is we just project away the first t components of a transition. We throw them away. If the formula has a for all instead, we transform it by using a common law of logic that says for all p is the same as there does not exist not p. And this might involve something called the subset construction, which I won't go into. But the important point is that such a construction could blow up the size of the automaton and make the number of states much, much larger, exponentially larger. And that is a deficiency in this. So finally, we can parse this formula phi. We use these well-known constructions on automata to implement the various operations, like logical operations. At the end, if there are no free variables in the formula, then we get a one-state automaton that either accepts everything, in which case we say proposition is true, or in that case we say it's. On the other hand, if the variables, that is, not bound by any quantifier, then at the end what we get is an automaton that takes t-tuples as input. And what does it accept? It accepts those t-tuples that make the formula evaluate to true. Now, the bad news is that the worst case running time of this algorithm is truly, truly awful. It can be something like 2 to the 2 to the 2 to the 2, all the way up, where the number of 2's in this tower is the number of quantifier alternations. And at the very top, there's some polynomial in the number of states needed to describe a sequence. And this bound can be improved to be double exponential. But the good news is that Nondeterminism for the particular logic that we've talked about, then it also applies to a much more general case, namely a case where we're talking about not just n plus, but a more general theory where we add the ability to compute this function, vk of n, which is the largest power a dividing n. In this case, exponent disappears and we get a worst case like this again. And this is based on this beautiful logical theory that's due to people like Bushi and Véronique Bruyère, George Hansel, Michaud and Villemer, and so forth. I won't list all the people involved because there are many. And the amazing thing is, despite the fact that we have this terrible, terrible bound on the worst case running time, an implementation often succeeds in a reasonable amount of time and space. And so now here's the good news, is that we can actually implement this and prove many old results from the literature and many new ones. Okay, so what can we prove things about? What sequences of over a finite alphabet can we prove things about? And one large class that this method succeeds on is the class of K automatic sequences. So what are these sequences? These are infinite sequences generated by an automaton, and as follows. Here's how it works. If you want to compute the nth term of the sequence, you represent n in some fixed integer base. The automaton reads the input, moves from state to state. Eventually, the last symbol of the base k representation of n is read, and we get to some state that has an output letter associated with it. And this output letter is the output a sub n. Okay, so the canonical example of this is something called the 2A Morse sequence. So in the 2A Morse sequence, we have some sequence of bits, zeros and ones. And it looks like this. And what is this sequence defined by? It's the number of ones counted modulo 2, or the parity of the number of ones, in the base 2 expansion of n. So for example, if we want to know what's the parity of the number of ones in 7, we go 1, 1, 1, which is the base 2 representation of 7, and we end up in this state 1, which says they're an odd number of ones. If we wanted to do it for 5, we'd go 1, 0, 1, and we'd end up in 0. That means they're an even number of ones in the base 2 representation of 5. So this is one of the simplest possible automata. And with our decision procedure, which has been implemented by students of mine in a program called Walnut, we can use this to rigorously check assertions about this sequence and many other sequences just by phrasing the assertion in first order logic. So let's talk about the 2A Morse sequence. Here are pictures of 2A on the left, Norwegian number theorist, Marston Morse on the right, American mathematician. After the sequence is named after these people. 2A was probably the first to study it explicitly, and Morse independently rediscovered it in the context of geodesics. So what can we do with this decision procedure? Well, we can give new, almost trivial proofs of famous old results. And sometimes these famous old results have only complicated or case-based proofs. We can check existing claims in the literature and fix wrong ones. We can improve previously known results. For example, we can turn an if into an if and only if. And we can explore new claims and obtain new results purely mechanically, just by stating the properties of the object we want, finding a procedure that will guess possible examples of this object, and then prove the properties we want with our decision procedure. And I've had the luxury of collaborating with some excellent people whose names are listed here and many others. So these results are due to various subsets of us. Okay, so let's look at this result about the 2A Morse sequence that I was talking about. What did 2A prove in his 1912 paper? He proved that this sequence of zeros and ones has an amazing property where it avoids various kinds of repetitions. And the most famous kind of repetition that it avoids is something called the overlap. Now, what's an overlap? An overlap is a string of the form AX, AXA, where A is a single symbol and X is a possibly empty word. So if we think of this as AX followed by AX followed by A, it's two consecutive blocks followed by the first letter of the blocks. So an example is the English word alfalfa. Here we have two blocks, ALF, ALF, and then an occurrence of the first letter of these blocks, A. So that's an overlap. 2A proved that this sequence is overlap-free. So that means it contains no contiguous block of symbols that is an overlap. So let's look here. We can see some squares, that is, blocks that are repeated next to each other, 1, 0, 1, 0, for example. But then the next symbol is a 0 and not a 1. If it were a 1, we would have an overlap, but there are no overlaps. And similarly, 0, 0, if it were followed by another 0, that would be an overlap, but it's not. So let's try to prove 2A's theorem by phrasing the existence of an overlap as a logical statement in our logical language. So what would an overlap look like? An A, a string X, an A, a string X, and an A. If this occurred at position I, and the length of the block AX were N, then the next A here, pointed to by this arrow, would be at position I plus N, and this A would be I plus 2N. And from here to here would equal all the X, A, AXA. So there would be integers I and N such that the symbols from position I to position N would agree with the symbols from position I plus N to I plus 2N. And we can express this in first order logic by saying there exists an I and an N such that N is greater than or equal to 1, because here A is a single symbol, so AX has at least one symbol. And for all J less than or equal to N, T of I plus J is equal to T of I plus J plus N. So here, when J is 0, it says Ti is Ti plus N. When J is N, it says Ti plus N is Ti plus 2N, which is exactly what we want. Okay, well, now we can evaluate this assertion, which the assertion is saying is an overlap. So what do we expect that to be false? T does not contain an overlap. We can type this in a system Walnut using exactly this command. So if you cut and paste and type this into Walnut, this will give you the result you're expecting. It says eval, so evaluate something. Here's the name that we're giving it, TM, 2A Morse, has overlap, has over. There exists I and N. Well, we don't have this backwards E symbol, so we just use the ordinary E. Exists I and N such that N is greater than or equal to 1, and we use the ampersand for and. For all, well, we don't have the upside down A, so we write it as capital A, J. J less than or equal to N implies Ti plus J is Ti plus J plus N. So as you can see, I'm going from a straightforward logical system in ordinary mathematical notation to something that looks almost exactly like it, with some nods to the fact that these symbols don't appear on the keyboard, so we have to do the best we can. And here's what happens when we do that. Here I've typed it in. Here's what Walnut responds in its verbose mode. It gives you various information about how much time it's taken and the sizes of the automaton it's getting by manipulating the formula. It says the total computation time was 523 milliseconds, which is half a second, and it says false. So the assertion was that 2A Morse has an overlap, and the result is that it does not. This is false. It has no overlap. So we've proven with this. This is a rigorous proof then that the 2A Morse word has no overlaps. Okay, well, let's look at another example. So Françoise de Jean in 1972, she wrote a famous paper where she gave an example of an infinite word, not this time over a 3-letter alphabet, with the optimal avoidance property for 3-letter alphabets. Namely, it avoids something called 7/4 plus epsilon powers. So what's a 7/4 plus epsilon power? It's a word of the form x prime, where x prime is a prefix of x, and the length of x prime is greater than 7/4 times the length of x. So what this is a block, and then a block that's just a little bit more than 3/4 the length of the first block that agree on the positions that they have. And the way she did this was she generated it by starting with the symbol 0 and applying these transformations over and over again. So if you look at her proof, it's rather complicated. Here I have some excerpts of her proof from her original paper. There are some figures and diagrams showing how the symbols change. She used A, B's, and C's instead of 0, 1s, and 2s. Here's a long argument in French with various cases that need to be discussed. We can get rid of all that. We can just type in the statement. So here I have to say what base I'm working in. And because the way she constructed her sequence used a map from 1 letter to 19, it turns out we need to use base 19. So this bit of gibberish at the very beginning is telling Walnut that you should evaluate this statement using base 19. And then we just once again say, well, there exist these I and N such that for all J, some property holds about the sequence, and it says false once again. So there are no 7/4 plus epsilon powers. And this one took a little longer. This took 79 seconds to compute. So a non-trivial computation, but it shows the kind of power that Walnut has. We don't have to go through this very long and complicated case-based argument. We can just type it in and get the result. Let's look at another example. Here's where we can use Walnut to check existing claims in the literature. So a recent preprint said, every segment of length k, that means a block, a consecutive block, of length k of the 2A Morse word is a factor, that means appears as a subblock, of every segment of length L equals 8k minus 1 of t. So we can check this claim. And I won't bore you with the translation of how this becomes this, but if you look at it carefully, you can see that this is asserting the same thing as this is. And now we have a for all I, j, and k, and there exists p, and a for all s. So it's a little bit hard to take in all at once, but you can check that this is saying the same thing. Here's the 8k minus 1 right here. And when you type this into Walnut, you discover that it returns false. So this claim from a recent preprint was actually wrong. And I pointed this out to the authors. But we can do even more with Walnut. Not only can we say, hey, this is wrong, we can figure out for which k it's correct. So if I remove the for all k, which was the assertion here, for every segment of length k, here's a for all k. Remove for which k it's true, and here's the result. So here you see I remove the for all k. Everything else is the same. What Walnut produces here is this automaton of 10 states, and it accepts the base k representation of those k for which the statement is true. That's the double circle. So we see it's true for length 1, 2, 3, 4. But if we try 10 in base 2 is 1, 0, 1, 0, then this state does not have a double circle. And so the claim is actually false for k equal 10. And in fact, if you follow this path and go here, and then here, 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 and then back again, you will see there are infinitely many k for which it's false. Okay, now I promised that you could improve previously known results. Let's see how it can do that. Well, to do that, I need to introduce you to some combinatorics on words terminology. And a word is bordered if it can be expressed as UVU for some words U and V with U non-empty, and otherwise it's unbordered. So an example of a bordered word in English is the word ionization. It has the border ion. It begins and ends with ion. So Curry and Sari proved that if we look at this 2A more sequence T, then it has an unbordered block, contiguous block called a factor, sitting inside it of length n if n does not leave a remainder of 1 when you divide it by 6. So for example, of length 2, 3, 4, 5, 6, those are okay. 8, 9, 10, 11, 12, those are okay. There's an unbordered factor of those lengths. But they didn't resolve the case of when n is 1 mod 6, when it leaves a remainder of 1 upon division by 6. And indeed, their characterization was not an if and only if, because here's an unbordered factor of length 31, and 31 is not congruent to 1 mod 6. So we'd like to know what are exactly which lengths does T have an unbordered factor. And luckily, we can express this property that it has an unbordered factor of length n as follows. First, we have a formula that says that the length n factor starting at position I has a border, and here's the assertion. Basically, this says that the block of symbols at the very beginning matches the block of symbols at the very end of the word. And then we just make the assertion that there exists an I that is not, that's the not symbol, bordered of length n. So we can just translate this into all pieces. So for formula for this, and then I call the formula with this $ syntax. So I use this to translate this. I say there exists an I such that not, there's the not symbol, bordered IN. And what do I get? Well, if you look at this, you see that the n is a free variable. It is not quantified. So we're going to get an automaton that's going to recognize those base 2 representations of n for which the statement is true, for which it has an unbordered factor. Well, first let's check their theorem. For all n, if 1 is not equal to n mod 6, and here's how I do n mod 6, n minus 6 times the integer division of n over 6, then I get an under of length n, and it says true. So their theorem is correct. But now we can do more. We can find all the n for which there's an unbordered factor, and it gives us this nice small automaton. And if you study this automaton, you see that the only way the n is not accepted is to get to state 4. And furthermore, the only way you can get to state 4 is by taking a path that looks like this. 1, 0, then 1 any number of times, then 0, and do that as many times as you want, and then a 1, and then a 0 any number of times, and then a 1. That's the only kinds of paths that will take you to state 4. And so finally, we get the final result. 2A more sequence has an unbordered factor of length n, if and only if the base 2 representation of n is not of the form 1, 0, 1, star 0, which is like saying 1 repeated any number of times. This whole thing repeated any number of times. 1, 0 repeated any number of times, 1. And that gives us an if and only if statement. Now that would be the kind of statement it might be hard to prove by hand. A lot of cases you would have to check. Even the original Curry-Sari theorem took a couple of pages with a lot of cases. So this is now an if and only if. It's probably harder. But Walnut can do this in a matter of just a second or something. Okay, let me just look and see how the time is going. Maybe I will, okay, I'll do this real quickly. This is, you might say at this point, well, okay, good. You can verify stuff that's already known. You're not really doing mathematics. You're just checking other people's stuff. So here's how Walnut was used to prove a completely new result. And for this completely new result, no other proof is currently known. So I need to introduce this notion of reversal of a word. So for example, to reverse a word means to read it backwards. So if I take the English word stressed and I reverse it, I get the English word desserts. So what I'm interested in is avoiding a pattern, having an infinite word that avoids some pattern, the pattern XXX reversed. And there doesn't seem to be many English words that have this pattern. The only one I could find is the rather odd word be pepper, which is a word and might be used in the context of ordering a pizza. And you say, aha, the pizza is bepeppered with pepperonis or something like that. But it's a rather unusual word, I admit. It has the pattern XXX reversed here in red, where X is EP. And the question is, are there infinite binary words avoiding this pattern? Well, it's easy to find, in fact, that there are such words. For example, the word 010101 forever avoids the pattern. We can see this, right? Because if it had a pattern of the form XXX reversed, either X would be of even length, in which case you'd get a number of repetitions of 0101, followed by some repetitions of 0101, but then the next couldn't be X reversed because that would be 1010. So that would force two ones in a row. And if it's of odd length, then the first repetition would be X and the second would be X, but one would begin with one symbol and the other would begin with the other. So that's not possible. So the question is, are there any other periodic infinite words? And are there any aperiodic infinite words avoiding this pattern? Aperiodic means no repeated block that just goes on forever. So in fact, there are, and I'll skip some slides here. It turns out that it's not too hard to find a plausible aperiodic infinite word, which I'll call RF. And the question is this an automatic sequence? And the answer is a little surprising. It's not automatic if you use base 2 or any other integer base, but it is automatic if you use some rather exotic way to represent numbers. And this exotic way is the so-called Fibonacci or Zeckendorf representation. So let me remind you what this is, or tell you what this is if you haven't seen it before. First of all, the Fibonacci number is one of the most famous sequences of all of mathematics. F0 is 0, F1 is 1. Each term is the sum of the two preceding. So we can write integers in Fibonacci representation by writing them as a sum of Fibonacci numbers instead of sum of powers of 2. So we write it as a sum epsilon I, fi plus 2, where these epsilon i's are 0 or 1. So I either take a Fibonacci number or I don't. The problem with this then is that some integers have multiple representations. For example, 14 you could write as 13 plus 1, and 13 and 1 are both Fibonacci numbers. Or you could write it as 8 plus 5 plus 1, and all of these are Fibonacci numbers. Or you could write it as 8 plus 3 plus 2 plus 1, and all of those are Fibonacci numbers. What we'd like is to have a unique representation, just like we do for base 2. So we impose an additional condition. Namely, we never use two Fibonacci numbers that are next to each other. So 8 and 5 are adjacent, which means that 3 and 2 are adjacent, which that's not okay. And then we write this representation by writing down the epsilon i's, which are ones or zeros. So 19 is represented by 10101, which means 13, 5 plus 1. This is called Fibonacci or Zeckendorf representation. Okay, so now we can make a finite automaton that instead of taking n in base input, takes the Fibonacci representation of n as input. Here's an example, the Fibonacci infinite word. This is a different infinite word. It can be accepted by a very simple automaton. All right, so what's the Fibonacci decision procedure? Exactly the same as before, as we talked about, except that all integers are represented in Fibonacci representation. We need some ability to check addition, like we did for base k. It turns out that there's a 17-state automaton that can check this. And this idea, using this is based on ideas originally due to Jean Berstel and since elaborated on by others like Christian Prunier and Jacques Sakharovich. So it turns out that our word that we stumbled across is generated by a Fibonacci automaton of 8 states. Here it is. And the output of each state is after the slash. So for example, if we want to compute the 0, 1, 2, 3, 4, 5, 6 symbol, we represent 6 in Fibonacci representation, which is 5 plus 1, which is the string 1, 0, 0, 1, and we go 1, 0, 0, 1, and we get 1, which is indeed the correct answer. So now we can prove that this string avoids the pattern XXX reversed, and we just implement the existence this has logical formulas for Walnut to handle. This one checks that one block is equal to the reverse of another. This one checks that 2 blocks are the same, and then I say, is it the case that it ever contains blocks next to each other that are the same? And then the second block here should equal the reverse of the third block. And that's what this checks here. And when we run this in Walnut, it reports false. And so this pattern doesn't occur. And similarly, I said I wanted an aperiodic word. We can prove that this word is not periodic with a simple logical formula. So this gives us a new result then, that in fact, no other proof of this is currently known. Okay, now I want to finish up by talking about the best possible research methodology with a little question mark. It's subject to dispute. Suppose we want to look for some object like what we just looked for, an object, an infinite word that contains no existence of this pattern, XXX reversed. Wouldn't it be nice if we could just desire a guesser that creates candidates for the words that you want, run this candidate through a checker to prove it, and if so, you have both the construction of the object and a proof of its correctness. So the advantages to such a thing would be mathematics becomes no work at all. You just state the desired properties of the object you want, and the program finds an example and proves its correctness. Disadvantage is then having to explain to your chair of your department why you should be paid to do mathematical research when it's that easy. Okay, so how do we get this magical thing that will create objects that we want? What we do is we have some sort of search procedure, a depth first or breadth first search over a space that has a decision procedure. And this depth first or breadth first search will figure out a good candidate for a solution. So I'll illustrate this idea with the Dean words. The Dean words are words over a 4-letter alphabet, X, Y, X inverse, and Y inverse, that have no squares in them. So that means no 2 consecutive blocks that are the same and are not reducible. There's never X next to an X inverse or a Y next to a Y inverse. So basically, we're looking for something in a free group that's reduced. So now we can code this. Walnut doesn't like dealing with things like X, Y, X inverse, and Y inverse. We have to code them as symbols. So we'll code X as 0, Y as 1, X inverse is 2, and Y inverse is 3. And what we can do is use something I call automatic breadth first search. What is this? How does this work? You guess that there is this object that you want. You guess that it's K automatic, so there's some base K automaton that will generate it. And you guess that the automaton has less than or equal to L. Just heuristics, which could be changed easily. And in fact, the program could go through lots of different possible combinations of K and L. Then you use breadth first search to explore the tree of all finite words obeying these constraints, such that the smallest automaton generates the word has less than or equal to. And if you're lucky, this breadth first search will converge to prefixes of a single infinite word or a small number of such words. So when we do this for Dean words, the breadth first search quickly converges on this string of symbols. You'll see that it never has a 0 next to a 2 or to a 3. and it never has two blocks that are the same. So 3, 2, 1 is not followed by 3, 2, 1. There's another 3, 2, 1 over here, but it's not immediately followed by it. And then we use something called the Myhill-Nerode theorem from automata theory to guess this as an automaton, or in other words, a fixed point of a morphism. I won't go into details of that. So then we can make an automaton with Walnut commands corresponding to this morphism, and we can check to see whether there's a square. Here, this checks to see whether there's a square. And we can check to see whether there's a 0, 2, 2, 0, 1, 3, or 3, 1. And all of these return false. So there we prove the existence of the Dean word with essentially no human intervention. We just said, these are the properties we want. Find a candidate with breadth-first search. Once we have the candidate, prove that the candidate is correct. So I think I will, getting down to close to the end of the talk, so I think I'll skip some things. So, but I do want to say that I view this idea of using decision procedures to prove things in mathematics, especially things for which there's no known simple proof, or for which the description is very, very complicated. I view this as a kind of powerful telescope. And here I'm taking a quote from a paper from 1932 written by D.N. Lamer about the invention of his son, Derek Henry Lamer, of a machine that would factor numbers. It would be very difficult to factor existing technology of 1932. In this paper, he said, the vast distances and vast numbers of the astronomer stagger the imagination, and yet the mathematician reaches out with his high-powered machines and his high-powered theorems and investigates the internal structure of his distant bodies, we might say these infinite sequences, much as the astronomer inquires into the structure of some distant star. Okay, now I have to confess there are inherent limits to what we're talking about. I'll just give one example. If we have a sequence which is generated by iterating these rules, then we might hope that we could carry out the same kind of decision procedure on a word like this, but unfortunately, we will never be able to. And the reason why is because this word encodes in the positions of the B's the characteristic sequence of the square numbers. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, then 16, 25, and so forth. The B's are positioned in the square. So we wanted to look at the first order theory of the natural numbers with addition and the ability to compute the nth term of this sequence. We would be able to say n is a square. And once we have that, we can say n is x times y for arbitrary integers x times y. And once we have that, the first order theory becomes undecidable. And so they're going to be very simple to describe sequences for which we're never going to be able to have a decision procedure. Okay, I'll just mention that if you want to play around with Walnut, it's free, publicly available. You can download it from this URL and play with it. Let me know if you discover anything good. And I'll just finish up tonight by giving my thanks to the designers and implementers of Walnut, Hamoun Mousavi, the original designer and implementer, and two additional students that I've had that have implemented additional capabilities, Asim Baranwal and Langdon Burnett. So thanks for all your attention. I hope there wasn't too much lag on the internet, that you were able to get something out of the talk. And thank you again for this very nice invitation to speak for you.
Yeah, thank you very much for this interesting talk. And I give now to the audience whether they want to ask questions.
So this was a really lovely talk. When you take this lovely walnut and present it to, well, I don't know, maybe your grandmother is not around any longer, but your mother or your aunt, what would be your favorite example of showing how great it is?
Well, I guess I have a lot of affection for this XXX reversed result, because it was something that we had discovered candidates to avoid this pattern for a long time, and spent many weeks trying to prove it by hand using the existing techniques. And we weren't able to do it. It had too many complications. I proposed to my student, well, there is a decision procedure for this. I pointed out to the student. So at least in principle, we could prove it by building a program for the decision procedure and consider doing this. And the student said, sure, I'll do that. And went off, and a month later came back with this program, and we typed it in, and within 1 minute, we had the solution that we had spent months and months on. But not only that, we had this incredibly powerful tool. So that ended up being his master's thesis, and a lot of other people have used it. So it was, at the time, it was sort of crazy that this would be the fastest way to solve it, is to build a general decision procedure for a much larger theory and then apply it to the specific example. But it turned out that way.
Oh, this is cool. So this is somehow the lifting of the give it to a student to give it to a student for mankind, right? I like that.
Well, it's very kind of Hamoun. I mean, he could have, it's his own intellectual work product. He could have licensed it or whatever, but he made it freely available to everyone.
Can you mention a mathematical result proved by Walnut that took a long time to? Oh
yeah, I can. In fact, I did skip over some slides, so I'll just narrate the content of the slides that I talked about. So people in combinatorics on words are often very interested in specific words, or archetypes of a whole class of similar words. And one of the words they're interested in is the so-called Fibonacci word. So Fibonacci is kind of an analog of Fibonacci, the Fibonacci word that I mentioned very briefly. And the way you can describe it is as follows. You start with the symbol 0, and then you replace in parallel for what you currently have, 0 by 0, 1, 1 by 0, 2, and 2 by 0. So it starts out 0, 1, 0, 2, 0, 1, 0, and so forth. So this is a string of 0, 1s, and 2s, and it has a lot of very interesting properties. So that's the first part. Now you have this Fibonacci word. The second thing people have studied, and this is much harder to study in general, is the so-called abelian properties of words. Abelian properties are those properties which don't depend on the order of the symbols, but just the number of such symbols. So properties that are invariant under permutation of the symbols. And finally, I can get to the point. An abelian cube is a block of 3 consecutive blocks of the same size. So let's say X, Y, Z, where X, Y, and Z are permutations of each other. So it's kind of hard to come up with a good word that's an example of this, but the English word deeded, D-E-E-D-E-D, is an abelian cube because it's DE repeated 3 times, but with permutations. So one could ask, which abelian cubes are there in the Fibonacci word? And this is something that is a natural question that combinatorics would have proven a theorem, and can be handled with Walnut. And when you do this in Walnut and you say, for which lengths are there abelian cubes in this Fibonacci word? The answer is, well, Walnut will take a very, very long time, on the order of hundreds and hundreds of seconds, if not several hours. I can't remember the exact amount of time, but it takes a very long time. And when it's done, it says, well, I can tell you what these orders are, and I represent them as a certain automaton, and this automaton has something like 5,000 states. So we get the answer it takes a while, and then the answer is that there isn't a simple description. There's this extremely complicated description. So that's an example of an answer to your question. And in general, I think we shouldn't be surprised at that. There's no reason why a simple to describe property should necessarily have a simple description.
Yes. Here's another question of from the audience. He asked, can one assemble a human readable proof from the Walnut proof? Or is it similar that the computer proof is so complicated, like with the 4-color theorem, that up to now nobody came up with a human understandable short proof?
So that's a very good question. Very good question. Can you assemble a human readable proof from the Walnut proof? And the answer is probably not. And the reason why is because the proof itself is given by this sequence of transformations on automata. And the only way to verify it, do those transformations, or to have a program that looks at the transformations you did and say, yes, I verified that those are the right transformation. It has to essentially redo them. So unfortunately, you don't get anything that's human readable, except in the most trivial of cases where you could compute the automata yourself. So I agree that that's a drawback, but my example of the abelian cube in Fibonacci shows that sometimes there's no alternative. There isn't even a simple way to state the result.
Yes, in another question, in the case that the Walnut differs from the published literature, were you able to track down the errors in the proof of the public literature?
Yeah, so this has only happened in a small number of cases so far, and it's always been something fairly minor, like an off by one error or something of that nature, where a subscript n should have been an n+1, and this was propagated throughout, that kind of mistake. So I'm not claiming that we've made any revolution in understanding, other than this is yet another tool that we can use to check at least some things.
Did you find a result to prove your findings about the Fibonacci work, what the Walnut does? Did you find a human proof for this?
No, we still haven't. No. But I would say that other people have also now looked at this avoiding XXX reverse. And so I'm thinking of results of Narad Rampersad and James Curry. They've proven very, very interesting results about the words that avoid this pattern, including counting how many finite words of length n avoid the pattern, and have discovered really unexpected results that, like, we've never seen before for pattern avoidance. So just even posing the question has led to a lot of other interesting mathematics. So if you've watched the background behind me, you'll see that the sun is slowly coming up here in Waterloo, Ontario, and it's the start of our day here.
Yes, so you have morning, we have evening here, it is already dark.
Right.
I would love to claim that these birds are here, but unfortunately they are not.
Oh.
For the automatic sequences, do you require that the representation of the natural numbers is a standard way, say, second of representation, or binary, or ternary, or decimal, or what? Or would you accept any automatic representation of natural numbers and addition as a base, and then take the words out with the automaton?
Yes, the whole thing should work for anything where the addition relation is computed by an automaton. So
okay. Yes, I was a bit interested in such things, but I have not yet any results. But if Walnut can work with this, it would be interesting.
Yeah, so So there's an alternative class of numeration systems called the Ostrowski numeration systems. And these numeration systems come up in the theory of Sturmian words, which is a vast subject combination. Basically, for any real number between 0 and 1, there's an associated Ostrowski numeration system that is based on the continued fraction expansion of the number. In this Ostrowski numeration system, it turns out that if you represent things correctly, you can add using an automaton. It's a little bit complicated to describe how it works. And this has been implemented in a rival system by mathematicians at the University of Illinois, Philip Hieronymi, which maybe you know the name, and his students and co-authors. And this rival system is called Pecan, and in this rival system, you can actually do quantifiers over uncountably many numbers. So for all real numbers, you can make an assertion about their properties of their Sturmian words. And he has been able to reprove some of the standard results about Sturmian words, and also reprove a result that we just published this year about Sturmian words. He was able to reprove this in his system. So that's really spectacular.
Yes, so that means he doesn't look at concrete sequences, but he makes that the whole class of sequences as reals and then proves results. So.
Right. In particular, a famous result about Sturmian words is that if you look at the number of distinct blocks of length n in a Sturmian word, it is always n plus 1. And this is the kind of thing that he can prove just by expressing this as the appropriate statement and for all uncountably many Sturmian words.
Okay, so we would end the formal part of this lecture. Then let's thank the speaker again.